principle of mathematical induction is a very, very important proof technique that is very, very common in mathematics. And the first time we look at it, it seems kind of confusing. So I want to introduce what it is, go over an example of it, and try to make sense of why induction is so useful. And so first, the statement of the principle of mathematical induction. Let's say that P of n is some sort of property or a statement that's defined for integers n. And we're going to let a be some fixed integer. Okay, so a is kind of our starting point. And we need two things to be true. So let's suppose the following two statements are true. One, P of a is a true statement. And two, for all integers k greater than equal to a, if P of k is true, then P of k plus 1 is true. So that second statement is a conditional statement. It's saying that if the kth iteration of this statement is true, then the truth of that statement implies that the k plus 1th iteration is true as well. Okay, so if you get both of those things, you get a starting point, and then you get this thing that says the kth one implies the k plus 1th one, then the statement P of n is true for all integers greater than equal to a. Alright, now the way you can think about this, the way I like to explain it is as dominoes. So you could have some sort of domino that we'll call P of a. So that's your first one. And I drew it this way because P of a fell over, right? So it's a true statement. Okay, so that's the first thing we assumed. Then we also said that, look, if the kth one is going to fall over, it not only falls over, it's going to knock down the kth plus 1th one. Alright, so the truth of the kth instance of my statement is going to imply something about the truth of the k plus 1th instance of my statement. The kth one's going to knock over the k plus 1th one. And if that happens, then guess what? They all fall. Now in the past I've had some students say, well, wait a minute, so what we're saying is we can just make up the kth statement and then have that say something. Well, that's not exactly true. We're saying here, look, hypothetically, if the kth iteration of this statement is true, then that's going to say something about the truthfulness of the k plus 1th statement. Okay, now I'm going to go over a very common example, kind of the basic example of induction, and I'm also going to show you the 5 elements that are very common to an induction proof. Alright, so let's go ahead and look at that. Okay, so here's my theorem. I'm saying I have a series written in sigma notation going from 1 to n of I. In other words, 1 plus 2 plus dot 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 all the way up to n. That sum is going to be n times n plus 1 over 2. Okay, and we're going to prove this through mathematical induction. So, proof. The first thing you want to say here is you actually want to state that you're going to proceed by mathematical induction. So I'm going to proceed, we will proceed by induction on n. Okay, and I'm going to keep up with, I said there's 5 elements to this. This is the first one. You want to have an introduction. Okay, so this is our intro. Now, if you remember in the statement of induction, we said that P of a is true. So in other words, for some starting point. Here, my starting point would be n being 1. That's the smallest integer I have in my sum here. So you can say, for example, if n is 1, then this summation going from 1 to 1 is just 1. And does that satisfy my formula? 1 times 1 plus 1 over 2 equals 1. Yes. So that means that our first domino fell. And what we call this is the base case. So you can say, so the base case holds. Alright, now labeling this 2, this is my base case. Now the next thing we need to say is we need to set up that if-then condition of induction that said if the kth iteration is true, that implies something about the k plus 1th iteration. So what we're going to do is say, hypothetically, let's let the kth domino fall down for some general k. Okay, so the way you could say that is, let's let k be greater than or equal to 1, and the summation going from 1 to k, which is 1 plus 2 all out to k, satisfies my formula, which would be k plus 1 over 2. All right, so this, what we've set up, is the third part of an induction proof, and this is your induction hypothesis. What the induction hypothesis is going to let us do is it's setting up that the kth domino has fallen over. Now we need to show that the k plus 1th domino falls over. And so a lot of times it's worth thinking about for a moment what that even looks like. So let's think for a moment. If P of k is k times k plus 1 over 2, what would P of k plus 1 look like? Well, that means I need to replace my k's with k plus 1. So that'd be k plus 1 times k plus 1 over 2. So that looks like k plus 1 times k plus 2 over 2. And somehow I need to be able to get this information from the fact that 1 plus 2 up to k equals k times k plus 1 over 2. I need all that, okay? So then let's say, then I know for a fact that 1 plus 2 plus plus k plus 1, okay, so that's the k plus 1th domino, equals something. What I know that it equals is k times k plus 1 over 2 plus k plus 1. Now wait a minute, how could I say that? How could I possibly say that? That's where induction comes in, right? I know by induction that 1 plus 2 plus all the way up to k equals k times k plus 1. K times k plus 1 over 2. So then 1 plus 2 plus k here is k plus 1 over 2. Okay. That's not the formula that I wanted, but let's see if I can get there. So if I get a common denominator here, that's going to be 2k plus 2 over 2, right? I just got a common denominator. So then I could combine these as k times k plus 1 plus 2 times k plus 1 all over 2. And now notice that I have two factors with a common term, and so I factor out that common term. So I'm being a little bit clever with my algebra here. End up with k plus 2 times k plus 1 all over 2. Wait a minute. Earlier when I was doing my scratch, that's exactly what I thought P of k plus 1 should look like. So here I started off with adding 1 through k plus 1, and I used the fact of my induction hypothesis to deduce that 1 plus 2 up to k was the same thing as k times k plus 1 over 2, and then I did some clever algebra and actually got the formula that I was looking for. Okay, this is the fourth and potentially the most important step of an induction proof that we call the induction step. Okay, and where did we actually apply the induction hypothesis is right here, going from that statement to that statement. And that is what makes this an induction proof. If you don't use the previous domino to knock down the next one, then you're not doing an induction proof. Okay, so now lastly we say, by the principle of mathematical induction, or a lot of times that's shorthanded as PMI, this restate your official statement. The sum going from 1 to n of I, which is 1 plus 2 plus all the way up to n, is n times n plus 1 over 2 for all n greater than or equal to 1. And there's the end of your proof. And this last part is the fifth part, and that's my conclusion. Okay, so let me run through this again real quickly. So I have my theorem here, okay, and I want to proceed by induction on n, so that's my introduction. So the way I do induction is that I need a starting point. In this case it's n equals 1, and I show that the formula was true for n equals 1. That's right here. I'll call this P of 1. Alright, so P of 1 worked. Now what I need to do this is say if P of k is true, then P of k plus 1 is true. So what I said is hypothetically, let's let k be greater than 1, and we get all that. And so that is P of k. So P of k is true, I need to show that P of k plus 1 is true as well. Okay, that's what I got to show. So I did that. I added up 1 through k plus 1, which is what I need for k plus 1, and then use the fact that 1 through k is actually this summation through the formula, did some algebra, and ended up with the k plus 1th instance of that formula. That's the induction hypothesis, is assuming that the kth domino fell down. The induction step is showing that the kth domino knocked down the k plus 1th. And then finally we have a conclusion. We say by PMI, our formula holds for all n greater than or equal to 1. End of proof. Induction is funny at first, and logically it doesn't seem like it should hold at first, but it actually is very logically sound and very, very powerful. If you have any questions, please let me know. I'd be glad to help. And please make sure you wrestle with this long enough to understand it, because you will need induction if you're going to study mathematics. And thank you for watching.